Deep learning architecture simplified. So here we will deal with CNN, RNN, GAN transformers and encoder decoder architectures. So let's get started. First is the convolutional neural network. Well, a convolutional neural network is a type of artificial neural network which is designed to process and analyze data with grid-like topologies such as images and videos. Imagine a CNN as a multi-layered filter that processes images to extract meaningful features and make prediction. Imagine you have a photograph of a handwritten digit and you want a computer to recognize that digit. So CNN works by applying a series of filters over that image, gradually extracting more and more complex features. So the first filter detects simple features like edges and line, while later filters detect more complex patterns such as shapes and digit. And this layer of CNN can be divided into three main types: convolutional layer, pooling layer, and fully connected layer. So what are convolutional layers? So these layers apply filters, also known as kernels, to the image. So each filter will slide over that image, computing a dot product between the filter and the pixels it covers. And this process generates a new feature map, which highlights specific patterns in that image. And this process is repeated multiple times with different filters, creating a set of feature maps that capture different aspects of the image. Second is the pooling layer. Now these pooling layers perform a downsampling operation on the features map, reducing the spatial dimensions of the data while retaining important features, which helps to reduce computational complexity and prevent overfitting. The most common type of pooling is max pooling, which selects the maximum value from a small neighborhood of pixels. Third is the fully connected layer, and these layers are similar to the layers in traditional neural networks. They connect every neuron in one layer to every neuron in the next layer, and the output of the convolution and pooling layers is flattened and passed through one or more fully connected layers, allowing the network to make a final prediction, such as recognizing the digit in an image. So in summary, we can say that a CNN is a type of neural network which is designed to process grid-like data such as images, and it works by applying a series of filters or kernels to that image, gradually extracting more complex features. And the output is then passed through pooling layers to reduce the spatial dimensions and prevent overfitting. Finally, the output is passed through fully connected layer to make a final prediction. Next comes the recurrent neural network. So these recurrent neural networks are a type of artificial neural network designed to process sequential data such as time series, speech, and natural language. Imagine an RNN or the recurrent neural network as a conveyor belt that processes information one element at a time, allowing it to remember information from previous elements to make prediction about the next element. Imagine you have a sequence of words and you want a computer to generate the next word in the sequence. So an RNN works by processing each word in the sequence one at a time and using the information from previous words to predict the next word. The key components of RNN is the recurrent connection, which allows information to flow from one time step to the next. The recurrent connection is a connection within a neuron that remembers information from the previous time step. And this RNN can be divided into three main parts: input layer, recurrent layer, and output layer. Now this input layer takes in the information at each time step, such as a word in the sequence, then hidden layer or the recurrent layer. It processes the information from this input layer using the recurrent connections to remember information from previous time steps. The recurrent layer contains a set of neurons, each with a recurrent connection to itself and a connection to the input at the current time step. And finally, we have an output layer which generates a prediction based on that information processed by the recurrent layer. In the case of generating the next word in a sequence, the output layer would predict the most likely word to follow the previous word in the sequence. So in summary, an recurrent neural network is a type of neural network designed to process sequential data. It works by processing information one element at a time using the recurrent connections to remember information from previous elements. And the recurrent layer allows the network to process the entire sequence, making it well suited for tasks such as language translation, speech recognition, and time series prediction. Next comes generative adversarial networks. So these generative adversarial networks, or the GANs, are a type of deep learning architectures that uses two neural networks, a generator and a discriminator, to create new realistic data. So imagine GANs as two rival artists, one creating fake art and the other trying to distinguish between real and fake. Now the goal of GAN is to generate high quality realistic data samples in various domains such as images, audio, and text. So this generator network creates new samples while the discriminator network evaluates the authenticity of the generated samples. The two networks are trained simultaneously in an adversarial manner, with the generator attempting to produce more realistic samples and the discriminator becoming better at detecting fakes. The two main components of GAN are generator. So this generator is responsible for creating new samples. It takes a random noise vector as an input and generate an output sample, such as an image or a sentence. The generator is trained to produce more realistic samples by minimizing a loss function that measures the difference between generated samples and real data. Then comes the discriminator. So the discriminator network evaluates the authenticity of this generated samples. So it takes a sample as an input and outputs a probability indicating whether the sample is real or fake. The discriminator is trained to distinguish between real and fake samples by maximizing a loss function that measures the difference between the probability of real and generated samples. The adversarial network of GANs arises from the competition between the generator and a discriminator. The generator tries to produce more realistic samples to fool the discriminator, while the discriminator tries to improve its ability to distinguish real from fake samples. And this process continues until the generator produces high quality realistic data that can't be easily distinguished from real data. So in summary, this GAN are a type of deep learning architecture that uses two neural networks, a generator and a discriminator, to create new realistic data. The generator creates new samples and the discriminator evaluates their authenticity. And the two networks are trained in an adversarial manner, with the generator producing more realistic samples and the discriminator improving its ability to detect fakes. So GANs have applications in various domains such as image and video generation, music synthesis, and text to image synthesis. The next comes the transformers. So the transformers are a type of neural network architecture widely used in natural language processing such as translation, text classification, and question answering. They were introduced in the seminal paper Attention is All You Need in 2017. So imagine transformers as a sophisticated language model that process text by breaking it down into smaller pieces and analyze their relationship. This model can then generate coherent and fluent response to a wide range of queries. Now this transformer consists of several repeating modules called layers, and each layer contains two main components. First is the self-attention mechanism. Now the self-attention mechanism allows the model to analyze the relations between different parts of input text. It works by assigning a weight to each word in the input sequence, indicating their relevance to the current context. This allows the model to focus on important words and downplay the importance of less relevant features. And second is the feed-forward neural network. So the feed-forward neural networks are multi-layer perceptrons that process the output of self-attention mechanism. They're responsible for learning complex relations between the words in the input text. So the key innovation of transformer is the use of self-attention mechanism, which allows the model to efficiently process long sequences of text without the need for expensive recurrent or convolutional operations, which makes transformers computationally efficient and effective for a wide range of NLP. So in simple terms, we can say transformers are a powerful neural network architecture designed for natural language processing tasks. They process text by breaking it down into smaller pieces and analyzing the relations between them through self-attention mechanism, which allows the model to generate coherent and fluent responses to various queries. Next comes the encoder-decoder architectures. So this encoder-decoder architectures are popular in natural language processing tasks. They are often used for sequence-to-sequence problems such as machine translation, where the goal is to convert input text in one language to its corresponding text in another language. So imagine an encoder-decoder architecture as a translator who listens to the person speaking in foreign language and simultaneously translate it to the listener's native language. This architecture consists of two main components. First is the encoder, second is decoder. Now this encoder part, it takes the input sequence and processes it sequentially, generating a compact representation often referred as context vector or contextual embedding. This representation summarizes the input sequence and contains information about its syntax, semantics, and context. The encoder can be a recurrent neural network or a transformer depending on the specific task and implementation. Then comes a decoder. Now decoder takes the context vector which is generated by the encoder, generates the output sequence, that is a target text, one element at a time. Decoder is typically a recurrent neural network or a transformer similar to the encoder. It generates the output sequence by predicting the next word in the target sequence based on previous words and the information contained in context vector. So during training, the decoder receives the true target sequence and its goal is to predict the next word in sequence. During inference, that is when the model is generating a response, a decoder receives the generated text up to that point and uses it to predict the next word. So in summary, we can say this encoder-decoder architectures are a popular approach in natural language processing tasks, particularly for sequence-to-sequence problems like machine translation. And this architecture consists of an encoder that processes the input sequence, generate a compact representation, decoder that generates the output sequence based on this representation, and this allows the model to translate input text in one language to its corresponding text in another language. Thank you.